Hello again. So in this session, we want to see what do each of these terms in the turbulent kinetic energy budget mean. Okay, so we want to investigate all these terms one by one. Okay, so let's first start with the first terms on the left-hand side of this equation. So we have the first term. The first term is partial k write it with scholar partial k over partial t. This is the first term. So what does this mean? This is basically rate of change of kinetic energy per unit mass due to non-stationarity of the flow, which could be because of the mean non-stationarity, unsteadiness of that, okay? So this is simply the rate of change of kinetic energy per unit mass. And then the second term, let's go to the second term. So the second term is uj partial k over partial xj, right? So what is this term? This is rate of change of kinetic energy per unit mass due to, it's not due to the non-stationarity, it is due to convection by the mean flow, right? So we have this convection here by the mean flow, and then this causes some change of kinetic energy per unit mass, okay? So these are the two terms on the left-hand side. So now let's go to the right-hand side, this term. Let's investigate what this term means. Okay, so let's go through that. So this term is basically known as turbulence transport term. Okay, so this is turbulence transport term. Okay. And let me actually, I have to also include the partial over partial xj here. The whole thing is called turbulence transport term. Okay, let's see what does this mean. This is actually transport of kinetic energy due to, the first one is due to the pressure fluctuations. So first, the pressure fluctuations can cause transport of turbulence. The second term here is just the turbulence itself. So the turbulence itself can also cause the transport of turbulence. And then the last term here is due to the viscous stresses. So the viscous stresses can also cause the turbulence to transport in the flow. Okay, so these terms have a property, that's why we call them turbulence transport term, and that is as follows. So imagine you have a box, and then the flow is in this box or in a domain that you are investigating, right, which is inside this box. Okay, so the property of these turbulence transport terms is that if you take the integral of these transport terms over the inside this volume, like let's say this is a control volume, and this is like the domain where domain is located, then we can, because this is a divergence term here, this is divergence term, because of this we can use the divergence theorem. So according to the divergence theorem, we can write the integral over this volume. Say if we have this volume here, of this quantity, partial over partial xj of this quantity, the whole turbulence transport term, of dv, because this is a turbulence, the divergence term. According to the divergence theorem, we can write this according to a surface integral. So instead of taking the integral over the volume, because we have divergence here, we can take the inside of the divergence over the surface of this control volume. Okay, so the integral over the surface, this equals to the integral over the surface of this term times the normal vector nj over the surface times ds, which is over the surface. Okay, so this is according to divergence theorem. We can remove this divergence and write these volume integral in terms of the surface integral. Okay, so assume the enclosure that we assume has rigid walls. So if this enclosure has rigid walls, then the normal vector of the normal velocity vector, which is going to be uj dot nj, is 0, right? If this is a vector here, this dot is going to be 0 on the surface, right? So if this is a rigid wall, we're not going to have any velocity components that are kind of normal to this surface. Okay, so if that's the case, then some of the terms are going to cancel out. For example, this term here, we know because we have delta ij, so this is p. When we multiply it by nj, then I should equal to j. That's the only component that will not be 0 based on the Kronecker curve delta. So p prime u prime j nj, if we take this bar, because we know that uj nj is 0, therefore this component is going to be also 0. And similarly here, we have this q square. This one is going to be also 0. Q square u prime j nj is going to be also 0 over the surfaces, right? Over the whole surfaces, these two are going to be 0. Also, if you assume no slip boundary condition, then the velocities themselves also are going to be 0, and the boundaries. This implies that the third term is going to be also 0, which is 2 nu Sij u prime I, because u prime I is going to be 0. So this term is going to be also 0 over the surfaces. So this means that this integral should be 0 over the surface. And what does this mean? This means that if you take the integral of all these terms, turbulence terms, transport terms, over the whole domain, and then you integrate it, the net effect of those will be 0. Right? So this means that net effect of this term, which is divergent term, in a flow is 0. Okay? So what it means that it basically, you have some terms, it just transport the turbulence from one part of the flow to another part of the flow. And if you take the integral of that, the net effect of it is going to be 0. So basically, it transports turbulence or energy, turbulent kinetic energy, from higher kinetic energy regions where turbulence is produced to lower KE regions. Okay. So this concept is very important, and it actually motivated a lot of modelers to simplify these terms and model these terms in terms of the gradient of the turbulent kinetic energy. Because as you see, these terms only take the turbulence, so kinetic energy, from higher to lower kinetic energy parts. So this means that they only are effective when we have a gradient in the turbulent kinetic energy, a spatial gradient in the turbulent kinetic energy. Okay, so many modelers use this concept and this kind of understanding to develop a simplified closure for this. So they say we can actually model these terms using an eddy diffusivity, say nu KE, multiplied by the gradient of the kinetic energy in space, partial xj. And this is actually effective eddy diffusivity. Okay, so this kind of model, this kind of turbulence closure, actually significantly, this closure significantly simplifies the TKE equation, right? Imagine instead of all these complex terms, you just write it here. You just write this term, right? You just write this term in the turbulent kinetic energy budget equation, right? So you just put it here. Put this here. It's going to be much simpler, right, now, instead of all these terms. So this is kind of one of the reasons we use these kind of turbulence closures to simplify these equations. Okay. So this was the first term that we learned, and now we want to go to the second term here in the turbulent kinetic energy budget equation. So let me write it down. The next term is this term. So this term is actually, we show this with P, this equals to P, and it's actually the production term, the turbulence production term. See what it is. So it's actually rate of production of TKE from the mean flow. So we briefly discussed this term, but in general, most of the times, U prime I, U prime J bar over partial Ui over partial Xj is negative. Okay, so I'm going to investigate this, why this is negative most of the times. Okay, so here, if you go, you see that this term is negative here, right? Is negative here and is positive here, right? And we know the term itself is negative, so it means that it's kind of adding to the turbulent kinetic energy budget here, and at the same time, it reduces the same amount from the mean kinetic energy budget, right? So what it does is that's why we call this turbulence production term. It means that this term fits turbulence and reduces the mean term. Okay. So this is important to note. And I'm going to show you one example of that. Okay, so say here we have a velocity gradient. So if you have a velocity gradient like this, a large velocity gradient in the flow, this is say velocity profile or like a jet or anything. Okay, so what does this term do is that when you have these large gradients, you have a lot of turbulence. So these large gradients are going to feed the turbulence. So they are going to increase the turbulence, and at the same time, they are going to reduce your mean velocity. So they are going to kind of smooth out your flow, smooth out your mean flow. So as time goes, this is going to be like this, and then finally it will be like this. Okay. So your gradient becomes smoother because your turbulence is getting higher, mixing gets higher, and then your mean flow is going to become smaller. Okay. So this is how this term is actually behaving. Okay. So now I want to show that in most flows this is the case. This is the case, and this term is actually the production term is positive in turbulence and TKE equation. So we have some situations that this becomes kind of, this term becomes negative, but most of the times this is negative. This is positive. This is going to be positive. Okay. So in order to show that, we can show it with this. So we can write the velocity, the mean velocity tensor, similar to the previous part that we wrote it in terms of a symmetric and anti-symmetric tensor for the turbulent part. We can also write this for the mean flow. So we can write this in terms of Sij plus omega ij, but now for the mean flow. And we know that this u prime I, u prime j is a symmetric tensor. It's a symmetric tensor. And this omega ij is an anti-symmetric tensor. So when we multiply u prime I by u prime j bar times ui u partial xj, this equals to u prime I, u prime j bar Sij plus u prime I, u prime j bar omega ij. And we know here we have a symmetric tensor multiplied by an anti-symmetric tensor, so their contraction is going to be 0, right? So contraction is 0. Contraction of symmetric and anti-symmetric tensor is going to be 0. So u prime I, u prime j times partial capital U over partial xj is going to be simply u prime I, u prime j, Sij. And we can actually model these Reynolds stress u prime j, u prime I, u prime j, using a simple closure, eddy diffusivity closure, where we have minus nu t Sij, right? Considering this closure, if we can write this closure for a flow, and this is right, if this is right, then u prime I, u prime j multiplied by ui over partial xj is going to be minus nu t Sij squared, right? Which is going to be, because this is positive and this is also a positive number, is going to be always negative, right? So this is kind of an informal proof that this term is going to be, most of the time in most flows, this is going to be negative. And so the production term here that has a minus sign of that is going to be positive here in the turbulence kinetic TKE budget, and it's going to be negative here in the mean kinetic energy budget. Okay, so this is production term. And finally, the only remaining term is that we are left with is the dissipation term. So 2 nu Sij bar, which we show it with epsilon is greater than 0, and it's actually dissipation term. So its rate of dissipation of TKE per unit mass due to viscous stresses. And in most turbulent flows, Sij bar is much greater than capital Sij bar. What does this mean? This means that the energy dissipation is mostly due to turbulence. So these small fluctuations actually lead to most of the energy dissipation in the flow, in turbulent flows, rather than those large velocity gradients, okay? So the mean gradients, right? So this was kind of the overall description of the terms in the turbulent kinetic energy budget equation. So let me briefly overview and review what we did today. So what we did is that we started with the Reynolds stress equation that we talked about in the previous lecture, and then we just substitute that K to I to get an equation for the fluctuating kinetic energy, which we defined as 1/2 of U prime I bar. And then, so this is the equation we got. And by some simplifications, we finally got this equation, which is the turbulent kinetic energy budget equation. And then here we wrote similarly an equivalent equation for the mean kinetic energy budget equation. And then we showed the meaning of these different terms. So the first term is rate of change of kinetic energy per unit mass due to non-stationarity. The second term is rate of change of kinetic energy per unit mass due to convection of the mean flow. And then on the right-hand side, we showed that these terms, these divergence terms, are actually called turbulence transport terms, and what they do is actually they just move energy or TKE from one part of the flow to another part of the flow, and their net effect in a flow is 0. Then the other term that we investigated is production term, and we showed that this production term is most of the times positive in the TKE budget and is actually negative in the mean kinetic energy budget. That means that this term feeds turbulence and reduces the mean flow term. And finally, we talked about the last term in the TKE budget, which is 2 nu Sij bar, which is actually known as dissipation term, and it's actually the dissipation of the turbulence due to or TKE due to viscous stresses. Okay, thank you very much, everyone.